Hello everybody. Today we're going to be going over the concept of separation of variables that are used to solve for PDEs. Separation of variable is a very fundamental method used to solve for PDEs. It'll be a basis for a lot of other methods that can be used that you'll probably learn later. So right now we're just going to go over a simple problem, and I'm going to kind of explain how to do the separation of variables as we go through the problem. So first of all, the reason it's called separation of variables is you're going to split your solution variable, in this case u, into two separate variables. One that is going to represent your solution for the x portion of u, and the other that's going to represent the solution for the h portion, for that t portion of u, which in this case is h. So once we have done this, we're going to plug it back into our initial function, in which case we have g. H dot is going to represent dh to t is equal to h times where dot is equal to d dt is equal to d squared dx squared. Okay. So then from here, if we divide by gh, we get 1 over h times h dot is equal to 1 over g times g double dot. It turns out the only way that we can have two independent variables, in this case h and g, equal to one another is if they are in turn equal to some other constant. In this case, we're going to call the constant c. So now, in order to solve these ODEs that we have here, we need to define what c is. So there are three cases that we're going to solve for. One is if c is less than 0, one if c is equal to 0, and one if c is greater than 0. We're going to start with the c is greater than 0 one. So if c is greater than 0, we have g double prime is equal to g times c, and then that comes out into this function here, which is a times the hyperbolic cosine plus some constant b times the hyperbolic sine for at cx. So now using our initial conditions, we have g of 0 is equal to 0, which results in a is equal to 0, which gets rid of that term. Then we have g of 1 is equal to 0, which gives us b times sinh of rad c is equal to 0. So now, here, we have two options. Either b is equal to 0 or sinh of rad c is equal to 0. If b is equal to 0, it becomes a trivial solution, which just means it is a solution that, while technically true because the coefficients are always 0, doesn't actually add into the final solution at all. It doesn't really influence the final solution. Or we could have sinh of rad c. If that is able to equal 0, then we can actually have a solution that counts towards our final solution. In this case, however, because we have defined rad c to be greater than 0, sinh of x is only equal to 0 at x equals 0, which means sinh of rad c cannot equal 0, in which case b equals 0 and we have a trivial solution. Now our second case we're going to look at is if c is equal to 0, in which case the solution to our ODE would look like this. which if we look at it, if we do g of 0 is equal to 0, you get b is equal to 0. If you do g of 1 is equal to 0, you get a is equal to 0. So this one just solves out to be a trivial solution. So now we have one last chance, in which case we are defining c to be less than 0. Now in this case, we have g of x is equal to a cosine of square root of negative cx plus b of sine square root of negative cx. And just to remind you, the reason it's negative c is because c is already defined as a negative. So when you're doing the solution, it'd be the negative of that constant, which in this case is some positive number, and the square root of that positive number. So now if we're to solve this one, we have g of 0 is equal to 0, which means that a is equal to 0. And you have g of 1 is equal to 0, which means that b is equal to 0, or sine of negative c is equal to 0. So if this is true, then it was a trivial solution, in which case this method isn't the appropriate method to use to solve this PDE. But if this is true, then we can use the separation of variables to solve this partial differential equation. In this case, because sine is a repeating function, which means it crosses 0 multiple times, you know that there is some value of n for which the sine of square root of negative c would be true. In this case, we have sine, we know that the square root of negative c needs to equal n pi. So c would equal negative n pi squared. So now we've solved for what our constant is, which is n pi squared. So our solution for g is g of x is equal to some constant that we do not know times sine of n pi x. Okay, so this is going to be important to remember. Now, we're going to solve for our h portion. So you have h dot is equal, or h dot over h is equal to c. So if we use our ODE methods, we know that this becomes ln of h is equal to c times t, which becomes h of t is equal to h naught times e to the negative ct, which becomes some constant h naught times e to the negative n pi squared t. So now that we have h of t and we have g of x, we can put it back together, and then u of xt is equal to g of x times h of t, which becomes b sine n pi x times h naught e to the negative n pi squared t. Now, this value here and this value here can be combined together to make some other constant. I'm just going to call the b tilde. And then we have this here. So, now that we have this value, we are left with two unknowns. We don't know exactly what values of n actually apply. It is totally possible that all n values are applicable, in which case our final solution would be some summation of values, in which case you would not get like u of x of t is equal to some constant times sine times e. You would have a summation of constants times the summation of sines times the summation of e's, where all these n values are separate values. However, in some cases, we can still do that summation, but we know that only one value of n is actually affects the overall solution, in which case all the other values would just be 0. And then the other unknown we don't know currently is the coefficient. So in order to solve for this coefficient, we need to use something called the Fourier coefficient, or it's also known as the orthogonality condition. And what the orthogonality condition states is that if you get the rule of sine, or a cosine would work too, if m equals n, which equals 0, it equals 0, equals 1/2 if m equals n, which is not equal 0, and it equals 0 if m does not equal n. This can be proved using some trigonometric identities. However, for the purposes of this problem, I will not go through that derivation. But this is essentially what it tells us. So if we look back at our other problem, we have u x comma t is equal to n equals 1 infinity of sine n pi x e to the negative n pi squared t. So we're going to use our initial condition now, which gets rid of the e term, so now if we multiply, let's see, if we, now in order to solve this b of n term, it becomes this. Where we know that this m value here is equal to 1 because there is no coefficient here, which would mean that this n value here needs to equal 1. So then our n value is 1, so it becomes 2 times 0 to 1 sine pi x dx. And you know that you don't need to test any of the other values of n because we are given a solution where only one m value exists, which in this case is m equals 1. So only n equals 1 needs to be tested. So in this case, when you do this here, this value is to 1/2. So 2 times 1/2 equals 1, which equals b1, which then you can plug back into your solution that we had before, which is up here, to get 1 times sine of pi x times e to the negative pi squared t. And that, my friends, is how you use separation of variables to solve a partial differential equation. Now, just to do a quick summary at the end of what I just did, first step is you define u, or your solution variable, as h of t and g of x, or, I mean, the h and g don't really matter, but you just need to define them as two separate variables when you're trying to solve it. 2 is use your initial conditions. Sorry. 2 is define 3 cases of C. 3 is solve ODEs with your boundary conditions. 4 be join H and G back into U. And then 5 is using orthogonality condition, which is also known as the Fourier coefficient, along with the initial condition, solve for the final solution. Yeah, so hopefully by following these steps, you are able to understand a little bit better how to use separation of variables to solve a homogeneous PDE. Some variations of this that you might see in the future is maybe the boundary conditions are not Dirichlet conditions, but they're von Neumann conditions instead, which just means that like the derivative is equal to 0 instead of the actual endpoints equaling to 0. That really doesn't affect very much other than this sign turn at the end might be something else depending on what initial conditions they give you. Yeah, so that's how you do that. More examples for how to use other methods of PDEs will be posted as well, but this is just kind of the introductory how to solve the separation of variables equation.